Hello ladies and gentlemen, my name is Carl Hasbrook, and in this video we will be looking at helper functions that we will use within our different search algorithms. Now this will be my third attempt in doing this because my first attempt completely failed. My second attempt did allow for the puzzle to be solved, but it had a really big memory footprint. So in this attempt of mine, I will be doing things a little bit differently. And as you can see, I changed my UI, added a bunch of buttons. None of them does anything right now because I removed all of that search functionality, all of the AI functionality, and I will be doing all of it from scratch. So first thing that we are going to do is we are going to create a static utilities class, which is going to contain all our helper functions. So in the scripts folder, we're going to right click, create C# script, and we're just going to call this utilities. And just go ahead and open that up in Visual Studio. And with our static helper class, we will be removing the start and update method, and we will be removing the inherit from mono behavior. The first thing we are going to do is, well, make it static. And now the second thing we are going to do is we are going to create another function for us to check if when state. This is going to look different from the one we made in our game manager for one reason. And in our game manager, we are using a list or an integer array or whatever to calculate the board and to do all of that. In our in the search algorithms, however, we will be using a byte array. This is going to lessen the memory footprint of the search algorithm by a lot. A reason I say this, if I go into calculator, is one byte is, a byte is a single byte. A integer is 4 bytes. So if we have a board state of integers, that'll actually be 36 bytes versus 9 bytes with the byte array. This is very important because as the algorithm goes on, the search space becomes exponentially bigger. And so if we minimize our memory footprint, that allows us to save on a bit of memory and performance. So our first method will be the check if when. So public static bool check if when, and for our parameter will be a byte array, and we will call it board. So just to get rid of that red squiggly, we are going to return a false for now. So now a few things need to happen. We need to go through every index within this byte array. Now this byte array will have a length of 9. So we can check if all the cells or if the value of an index corresponds with that index, then it is in the right position. If I were to open Excel and show you what I mean, let's say our board looks like this, or our first 3 tiles look like this. In position 0, we have a 0, which means yes, it is correct. If our first 3 looked like this, position 0 would have a 4, and that would mean that it's not in the goal state. So we only need to check up until we find one that's not in the correct position. So I'm going to turn this false into a true, and you will see now in a moment. You will see why in a moment. And then I will create a for loop from 0 to 9. And we will go through this byte array. So we are going to create an if statement, and within the if statement we are going to say if board at the I index is not equal to I, return false, because that means that we do not need to go further. We do not need to check all the other cells beyond this point. We can just say, listen, there is already one that's not in the correct place, therefore it is not within it is not in goal state. With that done, we will now create another helper function. This helper method is going to be a little bit more complex. We are going to get all the possible moves from a current board state. the reason for this is we are going to perform moves within a virtual space. And to do that, we need to figure out with a virtualized board what moves can be performed. So we are going to create the method public static list of integer as our return type, and I will explain why now. Get all possible moves or get possible moves, and then as our parameters, a byte array called board. So the reason I'm returning a list of integer is depending on what tiles can move, different amounts of possible moves can be returned. So a list of integer is a nice way to be able to return if there's only 2 possible moves or if there's 4 possible moves. So that's why I'm making it a list of integer and not something of a set length. So now the first thing we need is we need to figure out where on our board is our empty block. And for that, I'm going to create another method. And because we do not need to go any higher than, let's say, 255 in the search algorithm, I'm just going to return a byte because it does almost the exact same thing as an integer. Okay, so here is the main difference between what we're doing in our utilities and within our search algorithms than in our game manager. Because if you remember to previous videos, in our game manager, we represented the, for instance, in the calculate board method, the empty block as a -1. Now, we can't do that with a byte array because a byte is 4 bits of data and it can only hold positive integers from 0 to 255. So instead of making it a -1, I'm going to expect the empty block to be a, let's just make it a 255, since it's since the difference between a 0 and a 255 within a byte data type is negligible. There is no difference in the amount of space it will take up. So with that said, this method is going to require a for loop from 0 to 9 because there is, well, technically 0 to 8, but it is 9 iterations because there are 9 possible spaces for this to be. So if, okay, so I did not know that in a for loop you can use byte instead of int. I will, however, keep my eye on that because I'm not sure if it's going to work within the future or within the rest of the algorithms. So all we're doing is we're checking for all our from 0 to 9 within our board if that specific value is 255, which will represent our empty space, then yes, we have found our empty block. If for some reason we did not find 250, a good thing to do is to throw an error and return a simple value. So I'm just gonna right over here, going to return 255, and I'm gonna throw an exception, and I'm gonna say could not find empty block. And because it yells at me, because this is unreachable code, because as soon as this exception gets thrown, it will not continue with the code, I am just going to comment that out for now. So now we can figure out where our empty block is within our board. Now from there, over here, we need a reference or a placeholder for that. So what we're doing is we're creating a byte, and we are seeing, okay, listen, this is our empty block or the index of that empty block. And all we are doing now is we're using this method up here to tell us, listen, at what index is this empty block. So now we're really, well, it's not as complicated as a search algorithm, but it is a little bit complicated. We need to figure out where within the board our empty block is, and we're going to do that with a whole bunch of Boolean values, and I'm going to show you now how I'm going to do that. Now this might look really really weird. So all I'm doing is I'm creating a bool called TL, which represents top left, and all I'm doing is I'm setting it to the result of this comparison right here. So if empty block equals to 0, TL is going to be true. If not, TL is going to be false. And I'm just going to do that for all other 9 states of the board, or other 8 places within the board. Okay, so all I did is I created variables corresponding to all of the possible locations on the board, and I did a comparison for all of them. Now we know where our empty block is on the board. And how we will know that is only one of these can be true at a time. And that allows us to do a bunch of things. We are going to create a bunch of if statements regarding these and return the corresponding possible moves. So let's first get the possible moves that we can possibly take. So the way I did this, or the way I am going to do this, is with... Okay, so I'm going to hold the indexes of left, right, top, and bottom. What I'm going to do is I'm going to equal this to empty block minus 1. Okay, so I made a mistake there. The indexes of the position should be held in integers. Not that it's going to make a big difference, because there's not going to be a lot of these within our memory. So all I'm doing is I'm taking the empty block and I'm looking to what's of the left of it. Now how this works, if I were to open Excel again, is within our board, let's say we have 0, 1, 2. Let's say we are looking at position 4. Let's say that is our empty block with a value of 255. If we want to know what's on the left of it, we are going to look at position 3. So if our empty block is at position 4, 4 minus 1 equals to 3. The same with the right. If we want to look at what's on the right of our empty block, we are going to plus our current index by 1. Now, top and bottom is a little bit different. If we want to know what's on top of us, we minus by 3, and at the bottom, we plus by 3. And we are going to use this to figure out what indexes we can look at within our get possible moves function. Okay, so with that done, I'm going to create a placeholder list to hold all our possible moves. I'm just going to instantiate it with an empty list so we can add items to it. So now comes the really redundant part of this. We are going to need 9 if statements to check all of these Boolean values. And that is a lot of typing work, but it is what it is. So all I'm going to do for each one of these Boolean values is I'm going to see, okay, listen, I'm now looking at top left. So I can either move down or I can move right. And I'm going to add these values to the temp variable I created. And right at the bottom, I'm going to return temp, because that is going to now return all the possible moves from this board state we are looking at. So I'm just going to quickly add all the other if statements. Typing done, you will now see why I made it a list to keep track of all the possible moves. Mainly because as we go through all of these, you will see that depending on where the empty block is, we will have a different amount of possible moves. For instance, in the middle center, we have 4 possible moves, which means we can go left, right, up, and down. But if we were to go to the bottom right, we can only go up and to the left. And with that function done, okay, so we are going to create a last helper function. This helper function is going to be a check if contains. Because of the way lists and things work within C#, I decided to create a custom method for this. Okay, so in this method, we are going to try and see if a list of something contains something else. But we are going to tailor this to our program. We are not going to use generics. We are, even though that would be the proper thing to do, we are going to make it a really rigid, one purpose only type of method. So we are going to create, and as our parameters, we are going to add a IEnumerable. Now this is the class lists and queues and all those type of things inherits of. That will allow us to use this one method for queues and lists, and yes, we will be using both of those within later stages of this project. So now we have a byte array of item. So now what we are going to do is we're going to go through all the items in our list, and if we have an item that is equal or sequence equal to item, we are going to return a true, because we do not need to search any further. And so over here, I'm going to just return a false if it did not find anything. So the reason we are using sequence equal and not equal or dot equals or any of those things is I did a few tests over here within my game manager class. And let's say we have A and B, and theoretically data-wise, they both look the same. Originally, if you were to use list.contains, it would return a false. So that is why I did it like this. So I'm just going to run this just to show you why I'm using sequence equal to sequence equal instead of just dot equals or any of the other things. And as you can see, my utilities give me a true while the list.contains gives me a false. This has to do with how objects and equals and all those things work within C#. The dot equals is looking at a specific piece of memory or a specific instance of an object, and not necessarily what that object contains. So that is why we are using check if contains with a sequence equal. Okay, ladies and gentlemen, that should be it for this video. Any suggestions or questions, leave it in the comment section, and I will see you with the next video.